Hi everyone, welcome to the Week 9 lecture for Advanced Maths 1. So obviously this week, because of the public holiday, we don't have a class, so what I'm going to do is I'm going to run through the material for this week and then go through some examples for you to work on. Now just a reminder too, that if you're watching the videos and you didn't come to the other lecture, then you need to also submit the assignment for week 9, which you can find just under the links of these videos. Okay, so watch through the videos. Feel free to skip ahead, mute me if you don't want to listen to me, or look at the examples. Okay, and feel free to go back and rewatch the examples, etc. Once you've watched them and taken down the notes, okay, then have a look at the assignment question. Okay, and work through that. Remember, you need to write your answers on there, and you're going to hand that up to me in our next class in week 10. Okay. Now, today we're going to be moving on to a new topic, okay, which is calculus. Okay, so today's going to be a bit of an introduction. So there's going to be quite a few rules, and we're also going to introduce what the concept of calculus is. Okay, so let's get started. All right, so the first thing we want to talk about is the concept of what calculus is. Alright, so calculus forms a large part of our mathematics. Alright, I'll just check that you guys can see that. Yeah, that looks okay. So the concept of calculus, one of the easiest ways to explain calculus is that we are using functions to find other values on our functions. Alright, so far when we've looked at whatever function it is that we've looked at, okay, whether it's a quadratic function or an exponential function, okay, or a linear function, we know how to find the domain and range for these functions, okay, we know how to look at a particular value for an x value and find a y value, okay, but what calculus enables us to do is, as well as look at our functions, it enables us to find the slope of our functions, okay, and that's probably the biggest application of calculus. Now, with a linear function, like this one, we know that the slope is constant. So at any point, here, 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 anywhere on that line, the slope is a constant number, okay, so it's quite easy to find the slope of this line, all right, and so a linear equation might be something like 3x take 2, okay, and we know that this number here is the slope, all right, and that'll be the slope for any straight line. Okay. Now, when we have a function which is not linear, like a quadratic or a exponential function, okay, it's not as easy to determine the slope. And the reason it's not as easy is because the slope changes. All right, so for example, if we take this quadratic here and we look at this point, then the slope of this line, we can estimate it using a linear function, and we can approximate the slope. But if we then move to a different point, let's say over here, and then we approximate the slope again, you can see that the slope changes. All right? And as we move along this curve, the slope is constantly changing. So at this point, the slope is negative, and then up here it's really negative. Down at this point, the slope is flat or 0, and then the slope becomes positive. Okay? So the slope is constantly changing, and what we want is a way that we can work out the slope of a function so that we don't have to continually recalculate the slope. All right? So sure, I could take this point and I could estimate it with a straight line, but then that would give me the slope at one point, but not necessarily any other point. It would only be accurate for that one particular point. Now the same is true for the exponential function. As we increase, okay, the slope gets steeper. Okay. So the idea of calculus is that we want to be able to find a slope function. Okay, so we want to be able to find a slope function. All right. Now, if it's a slope function, we want it to be able to give us the function at any particular point. All right. So if we take our quadratic example again, okay, So let's say that we've got this function here, which is our basic quadratic function. Okay. So it touches at that point, and this is the function y equals x squared. Right? So we want a function which will find us the slope at any point along here. Alright? So that we can substitute numbers into it to calculate the slope. Alright? Now to do this, we're going to use a concept called first principles. Alright? So I'm going to pick a couple of points. So let's call this point x. Okay? Now, the y coordinate will be x squared, because I'm on the function x squared. Let's pick another point up here, and I'm going to call this x plus h. Alright, so this distance here is h, and this coordinate here will be x plus h squared. Okay. Alright. Now, if we draw a line between these 2 points, so from here to here, we will get an approximation of the slope at this point. Alright? Now this method here is called first principles. Alright? And we're going to look at how we find the slope using first principles first, and then we're going to look at a series of rules. Okay? So, if I was to estimate the slope, okay, so let's call this, as I said, first principles. Okay. Now we know that the slope is the y-step over the x-step. Okay. Now in our case, our y-step is the difference between x plus h squared and x squared. Here's our y-step here. Okay. And our x-step is x plus h minus x. Here's our x-step here. Okay. Now if we simplify this, we get x plus h squared minus x squared over h. Now, what we're going to do is we're going to use a concept called a limit to look at what happens. So, as we bring this point closer and closer down here, the approximation becomes more and more accurate for the slope at this point. Because remember, we're trying to find the slope at the point x. Now, what we're going to do, so we're going to say that the derivative or the slope function, okay, let's call it f dash x, okay? So f dash x is our derivative function or our slope function. So sometimes called the derivative. Okay? Alright? So our slope function will be accurate at this point as h gets closer and closer to 0. So what we're going to say is that f dash x equals the limit as h approaches 0, okay, of f of x plus h minus f of x over h. Okay? And this is our formula for using first principles. Okay? Now, if you haven't seen a limit before, basically what you're saying is that h is going to get closer and closer and closer to 0 until it's so close that it is basically at that point. Alright? Now, if you notice, if we let h go to 0 at this point, we'll have x plus 0, which is f of x, minus f of x, which is 0, divided by h, which is also 0. So we'll have 0 divided by 0, which obviously is not a logical number. Okay, so we can't let h go to 0 at this point. All right, but what we can do is we can do a simplification. So let's go back to our example, okay, which was this one up here. Okay, so if we've got the function y equals x squared, okay, then our derivative function or our slope function will be the limit as h goes to 0 of f of x plus h, so that'll be x plus h squared minus x squared divided by h. Alright, now at this point, so remember this here is f of x plus h, and this here is f of x. Now, what we're going to do is we're going to do a simplification, okay, to calculate the derivative. So, we're going to write, oh sorry, this should be h, my bad. So this should be the limit as h goes to 0. Now, if we expand this out, we'll get x squared plus 2xh plus h squared minus x squared over h. Alright? Now, at this point, if you've done your expansion correctly, you should notice that something will cancel out. Alright? I'll just go with a different colour text there. So you'll notice that the x squared and the x squared will cancel out. So all terms that don't include a h will cancel out. Alright, so what we've got is the limit as h goes to 0 of 2xh plus h squared over h. Now at this point we can also cancel out a common factor of h on the top and the bottom. So h. So we get the limit as h goes to 0 of 2x plus h. Alright, now at this point we can now execute our limit and say, so therefore as h approaches 0, f dash x will equal 2x. Because as h goes to 0, this term here will basically be 0. And so we'll be left with f dash x equals 2x. Alright, so this is our slope function for the function x squared. Okay, so now we can find the slope at any point on our curve. So for example, if we've got our quadratic, which is x squared, okay, now if we take a particular value, let's say this value here, which is x equals 3, okay, now when x equals 3, y will equal 9. Okay, we put 3 into here, 3 squared is 9. But if we look at f, so f of 3 is 9. Now this tells us that we're passing through the point 3, 9. And we've done that before. But if we do f dash 3, okay, we will get 2 times 3. So if we put 3 into the derivative, okay, we'll get 6. And this tells us that the slope is 6 at x equals 3. Okay. So the slope of the line, which is tangential here, okay, the slope of that line is 6. Okay. So what we've got now is a way that we can find the slope at any point. So we can take a value of x and we can substitute it into our slope function, and therefore we can find the slope at any particular point. All right. Now this method might seem like it's a little bit long, okay, and it is, and we're going to look at some rules in a minute and some shortcuts that we can do. Okay. But first I'm going to do another couple of examples of this because it is a requirement that you understand the concept of first principles. Alright, so even if you can do it an easier way, that's fine, but it's important also to be able to use this process. Now, a couple of other things that we might notice about this. So we've got our derivative, our slope is 6. Okay, so if our slope is positive, that means that we've got an increasing function. Okay, so the function is going up. Okay, if our slope is negative, then our function is going down. All right, the slope is the rate of change of the function. So if our slope is positive, it means we're increasing. If our slope is negative, it means we're decreasing. All right? If our slope is 0, it means we're at a minimum or maximum point or inflection. And we'll talk a little bit more about those next week. All right? But it's important to understand the difference between these two values here. So f of 3 is 9, and this gives us a point, a position. F dash 3 is 6, which tells us the slope at a particular point. Alright. Okay, so let's have a look at another example. So let's say we've got f of x equals 1 over 2x plus 1. And we want to find the slope of this function. Okay. So the first thing we do is we find f of x plus h, which is 1 over 2x plus 2h plus 1. So we've got f of x plus h, f of x. So our derivative, f dash x, is the limit as h approaches 0 of this minus this, divided by h. Okay? So using the same rule as before, f of x plus h minus f of x divided by h. Now, in this case, it's a bit trickier to simplify. Okay, so we can't simplify it straight away. We have to do a simplification. And we've got two fractions here. Alright? Now, whenever I've got two fractions and I want to add or subtract them, I need to find a common denominator. Now, I'm going to do the same thing here. And this is no different to if I was doing something like 3/5 minus 1/3. Okay? What I would do is I'd get a common denominator. I'd multiply this by 3 and this by 5. And this would become 3 over 15 minus 5 over 15. And then I can simplify this to 3 minus 5 over 15, which is minus 2 over 15. Alright? Now, we've done a lot of work with this sort of thing before, with fractions, but some people still find it a little bit tricky. Okay? So, even though this is more complicated, I'm effectively still going to do the same thing. I'm going to multiply this side by this, and this side by this on the top and bottom. Alright? So this will become limit h goes to 0. So multiply this up there, 2x plus 1, over, and this will be 2x plus 2h plus 1 times 2x plus 1, minus, and multiply this up here, 2x plus 2h plus 1, over 2x plus 2h plus 1, 2x plus 1. All over h. Now, it looks complicated, and I accept that it looks messy, alright? But now we've got a common denominator, so we can do this, subtract this, alright? And if we do that, you'll notice that we've got 2x minus 2x, cancels out, 1 minus 1, cancels out. And so what we're actually left with is a limit as h goes to 0 of minus h over 2x plus 2h plus 1, 2x plus 1, all over h. Okay. Now at this point, we can cancel out our factors of h, and we've got limit h goes to 0 of minus 1 over 2x plus 2h plus 1, 2x plus 1. Right. Now, once we've cancelled out our h's, then we can execute our limit. So now we can let h go to 0. So as h approaches 0, f dash x, so as h goes to 0, this h will cancel out. We'll have minus 1 on 2x plus 1 times 2x plus 1, which is 2x plus 1 squared. So we'll have minus 1 on 2x plus 1 squared. Okay? So this is our derivative function, okay, or our slope function. So we can now take values of x and put it into here and find the slope at a particular point. All right? Now I'm going to do one more example, and then we'll move on to looking at the rules of calculus. Okay? Okay, the last example I'm going to do is involving a surd function. Okay, so we're going to have f of x equals the square root of x take 1. Okay, all right, same process. I'm going to go through this one a bit quicker. So f of x plus h is the square root of x plus h take 1. All right, our derivative function f dash x is the limit h goes to 0 of x plus h take 1 minus x take 1 all over h. Okay. Now, similarly to before, we can't cancel out our x's yet, so we have to simplify this function in some way. All right. Now, to simplify our surd function, we're going to use what we call a conjugate. So you may be familiar with the fact that if you have the square root of a minus the square root of b, and you multiply it by the square root of a plus the square root of b, this will simplify to a minus b. Okay? So this is called a conjugate. All right? Now we're going to use this same concept up here. Again, it's a little bit more messy than this example, but same thing applies. So what I'm going to do is I'm going to multiply this function here by the square root of x plus h take 1 plus the square root of x take 1 over the square root of x plus h take 1 plus the square root of x take 1. Now, this whole thing is just equivalent to 1. Same on the top, same on the bottom. Okay, so I'm multiplying it by 1. So I'm not changing it, but I'm putting it into a format that's going to benefit me. Okay. So on the top line, when we use our FOIL rule to expand this times this, this times this, this times this, okay, we will have the same situation we had before, where we're multiplying this by its conjugate. So this will become limit h goes to 0, x plus h take 1 minus x take 1 over h times by, and on the bottom line we've got a bit of a mess, okay, like this. Now at this point you'll notice, again on the top line we cancel out, so x, minus 1, minus 1, and then we've also got h and h. Now just remember, when you cancel out something on the top line, you've still got 1 left. So this will be equals limit h goes to 0 of 1 over x plus h take 1 plus x take 1. And at this point, we can execute the limit. So we can say, as h approaches 0, f dash x equals 1 over, this will be 0, so square root x take 1 plus square root x take 1. So that's 2 of them, 2 square root x take 1. Okay? And we end up with our derivative function. Okay? All right, so you've got 3 examples there of how the first principles works. Now, obviously this method is a little bit tedious and it takes a little bit of time, and there are shorter ways, okay? And so what we're going to do now is we're going to look at a series of rules for calculus, okay? We're going to build on these rules not just in this course but also in advanced maths too. So, unless you're specifically asked to use first principles, we would expect you to use the rules that I'm about to go through. Alright? Unless, as I said, if you're explicitly told to use first principles, then use that method, otherwise use these ones. So, rules of calculus. Okay, so what I'll get you to do is to draw up a table. So we're going to have f of x here, and then we're going to have f dashed x here. Now, as I said, this is your first introduction to the rules of calculus. And as you go on with your maths, you will gradually add to this set of knowledge. Okay, so we're just going to look at the basic rules today. And as I said, you will build on this and look at more rules and more complex rules as you go. So, let's start with some simple ones that we already know. So for example, let's have a constant. Let's call it k. Alright. Now we know that a constant, if we look at the graph of a constant, okay, it's just a straight horizontal line. Okay, so the slope of this function would be 0. Okay, slope all along here is 0. If we look at a linear function, let's say kx plus c, alright, we already know this one as well, okay, so kx plus c, our slope is just this value here, which is k. So the first 2 rules are ones that we've come across. We wouldn't have called them rules of calculus, but that's what they are. Okay. Now our next one is if we have, and this is where it gets a bit trickier, if we have some sort of polynomial, let's say x to the n. This could be x squared, x cubed, x to the 4, any power of n. Alright. Our derivative, and again the proof of this you can use first principles, but our derivative is nx to the n minus 1. Alright? Now the easiest way to remember this is we take the power and multiply it out the front, and then we reduce the power by 1. Okay. Alright. So this is our rule for n. Now, this applies for all values of n. Okay, so don't get fooled into, for example, here, the square root of x, remember, is x to the half. Okay, so we could use this rule in this case. Alright, our 1 over x is x to the minus 1. Okay, so this is our value of n, this is our value of n. So we can find the derivative of these functions using this rule. Okay, people often forget that the square root of x is x to the half and 1 over x is x to the minus 1. Okay, these functions are all of this form. They can be written in the way x to the power of n. Okay, and we can use this derivative for all of these functions. Okay, now as well as these, we also have a number of other rules that apply if we have multiple functions. Okay, so let's say that we've got, let's call this g of x to the power of n. Okay. Now, this could be something like, for example, 3x squared plus 2 to the power of 7. Alright? So some function to the power of n. Okay? It could be the square root of 2x take 3. Okay? Because remember, this is 2x take 3 to the half. Alright? Now, in this case, we have to use what we call the chain rule. Okay? So the chain rule says this, that the derivative is n times g of x to the n minus 1, so just the same as this rule, but then we have to multiply by g dash x. And as I said, this one is called the chain rule. Okay. So, function to the n, multiply the n out the front, reduce the power by 1, same as this rule. But then we also have to multiply by the derivative of what's inside the brackets. Now, the next rule is if we have, let's say, u of x times v of x. Okay, so one function multiplied by another function. Okay. Or the product of two functions. So this one is called the product rule. And the derivative is as follows. So u dash of x times v of x plus u of x times v dashed of x. Okay? And this one is called the product rule. Okay? Now again, this looks a bit complicated, but in a minute when I go through some examples, it will hopefully be a little bit clearer for you. Okay? And the last one we have is if we have the quotient rule. Okay, so this is where we have one function divided by another function. Alright? Now in this case, our rule, similar to above, so u dash x times v of x minus u of x times v dash of x divided by v of x squared. Okay? And as I said, this one here is the quotient rule. Okay? So we've got the chain rule, the product rule, the quotient rule. Now with this table of derivatives, we have enough rules to be able to find the derivative of a series of different functions. Now, as well as finding the derivative, we can also find the nth derivative. So I could find the first derivative, or the second derivative, or the third derivative, okay? So to find, these help us find the first derivative. To find the second derivative, we just find the derivative of the derivative, okay? And I'll show you some examples of that in a second. All right, so there's our table of rules, okay? Alright, so let's work through some examples now. Alright, so I'm just going to work through maybe 6 or 7 different examples, okay? And then go through a couple of brief applications, and then that's basically it for today, okay? So it's really just about practicing derivatives. And you'll notice in the assignment and in the practice questions that I've basically just given you a whole heap of functions to take the derivative of, okay? Over the next few weeks, we're going to use these derivative functions, all right, and use them in problem solving, in finding slopes and tangents and normals and minimum and maximum and optimization and a whole range of different things. So understanding the rules and finding the derivative in each case is really, really important, okay? So I want you to follow along with the examples, but also practice some of your own examples too. Make sure you're familiar and you can use these rules, okay? If you can, the next few weeks will be much, much easier for you, all right? If you can't, you're going to have to spend some time, rather than learning the new material, you'll get caught up on not being able to take the derivative, okay? So from next week on, I'm going to assume that you can find the derivative, and it's going to be more about applying it. Okay, so I really want to emphasize how important it is for you to be able to calculate the derivative of a function. All right. So let's have a look at some examples. All right, so every one of these ones, we're just going to find the derivative. So here's f of x. So we've got 3x squared plus x cubed minus 2x, okay, plus 7. All right, I want to find the derivative. Now, when I find the derivative, I find the derivative term by term, okay? So I don't need to do the whole thing at once, I can do it one step at a time. All right, so f dash x. So let's take the first term here. So we've got 3x squared. So we're going to take the 2 and multiply it out the front. So that gives us 6x, and then we reduce the power by 1. So 2 take 1 is 1. Now, we could write 6x to the 1, but we don't normally do that, okay? So x to the 1 is just x, okay? So we would just leave it as 6x. Then we move on to our second term. So take the power out the front, 3x, reduce it by 1, becomes 3x squared. Now this one is a linear function. So the derivative of this is just the number in front of the x, which is minus 2. And then we've got 7, and the derivative of 7 is just 0, okay? Because 7 is a constant. All right, so that's our derivative, okay? That's our slope function, okay? Now, just before I do that actually, just a reminder that we can also find the second derivative, okay? So the second derivative is denoted f double dashed x, or sometimes it might be written as f2 of x, okay? So these represent the second derivative, okay? Now to find the second derivative, we're just going to take the derivative of the derivative, okay? So here's our first derivative, so now we're just going to find the derivative of this. So again, linear term, derivative of 6x is 6. Here we've got 2 multiply 3, so that's 6x to the power of 1, and derivative of minus 2 is 0. So this here is our second derivative, okay? Now theoretically we can keep taking the derivative, we could find the third derivative, the fourth derivative, etc. But in our case, and in terms of the applications, the main applications occur for the derivative and the second derivative, all right? There's not many further applications after that. All right, so we really focus on the first and the second derivative. All right, second example, and I'll gradually make these a little bit more complicated. So let's say we've got f of x equals 1 over 3x plus 2 cubed. Okay. All right. Now, the first thing you might notice is, okay, this doesn't look like of the form something to the power. Okay. Now, whenever I'm doing derivatives, I always try to write my functions as a power of n. Okay, so I would write this, instead of writing it like this, I'd write it as 3x plus 2 to the minus 3. Okay, remember, when we bring something up to the top line, the power is multiplied by minus 1. Okay. Now, if we look at our, sorry, I should say, we haven't taken the derivative here, we've just simplified the function into a different form, all right? So if I want to find the derivative, okay, I've got some function to the power of n. So I'm going to have to use the chain rule here, all right? So my derivative, f dash x, okay, so I start with the outside. So I take the number, multiply it out the front. So minus 3, 3x plus 2, and decrease the power by 1. So minus 3 minus 1 is minus 4. Okay. Then, that's the first part of the chain rule. The second part is I then have to multiply by the derivative of what's inside the brackets. So the derivative of this is 3. Okay, so I multiply by 3. All right. Now, if you like, you can simplify this, and this would become minus 9, and this would be 3x plus 2 to the 4. Okay. At this stage, I'm not too fussed about simplifying. Okay, if you want to leave your answer like that, that's totally fine. All right. So this is an example of the chain rule. Okay. All right, example number 3. Just check. So example number 3. Let's say we've got the square root, sorry, f of x equals the square root of x cubed plus x squared. Okay. Now again, write it as a power, so x cubed plus x squared to the power of a half. Okay. Just makes it easier and more obvious to see. Okay, so when we take the, again, haven't taken the derivative yet, just simplified. So if I take the derivative, f dash x, okay, again, I've got some function to a power, so I'm going to use the chain rule here. All right, so half comes out the front, x cubed plus x squared to the minus half. All right, so that's the first part. Multiply the power out the front, reduce the power by 1. Then I need to multiply by the derivative of what's in the brackets. Okay, so the derivative of this is 3x squared. The derivative of this is 2x. Okay. So my derivative function looks like this. Now again, it's a little bit messy, but I'm not too fussed at this stage. I'm happy for you to leave it in this form. Okay. So until we get to the point where we are problem solving, okay, there's really no need to simplify this. Okay. So this is an example of another example of the chain rule. Okay, example number 4. So this time we'll do a product rule. So let's say we've got square root of x times 3x cubed plus 1 to the power of 7. Okay. So I've got this times this. So as soon as I see that I've got two functions together, I know that I need to use the product rule. All right. Now what I'm going to do is off to the side over here, I'm going to say, okay, let's let u be x to the half. So that's this one. And let's let v be 3x cubed plus 1 to the 7. Okay, here's my u and my v for my product rule. Okay, so remember we had u times v, and then we had the rule, okay, for the derivative. So what I'm going to do is I'm going to find the derivative of these separately. So u dashed is a half x to the minus a half. Okay, so I found the derivative of this one. And then v dashed, now to find the derivative here, I'm actually going to need to use the chain rule within the product rule. Okay, and this will happen sometimes. All right. So my derivative, 7 out the front, 7, 3x cubed plus 1 to the 6. Okay, so multiply out the front, reduce the power by 1, and then multiply by the derivative of what's inside the brackets. Okay, so the derivative of this term is 3 times 3 is 9x squared. Okay, and then the derivative of 1 is 0. Okay, so this here is just kind of to help me. Okay, so now I've got it in this form. I've got u times v, all right, and I know that my derivative is u dash v plus uv dashed. Alright? And that's just straight from my product rule from before. So, all I now need to do, now that I've worked these out separately, is just substitute them into my formula. Okay, so it'll look like this. U dashed half x to the minus a half times v plus u times v dashed, okay, which is 7, 3x cubed plus 1 to the 6 times 9x squared. And again, it's quite long and messy, but at this point, I'm not fussed if you leave it in this way. Obviously, you could simplify some of these. You've got the 9 and the 7, you've got the x and the x squared and x to the half. But at this point, I'm happy if we can just find the derivative function. Okay. All right. Now, I find it really useful to do this section here, off to the side by itself. I find that easy just for me. That's just what I like doing. Some people will go straight from here to here. That's okay. It's completely up to you how you go about doing it. I guess the important thing is that over here, you're just doing one step at a time. Okay, so you're less likely to make a mistake. Over here, you're trying to put it all together at once, and sometimes that can cause mistakes. Okay, but it's purely up to you. If you want to go straight from here to here, that's okay. If you want to do this step, that's fine too. Okay, so it really doesn't bother me as long as you can get to the final answer. Okay, let's have a look now at a quotient rule example. Okay, so let's say that we've got f of x equals x plus 1 to the 4 divided by x squared take 3. Okay. So one function divided by another function, so that tells us that we should be able to use the quotient rule. Now I'm going to do the same as before, so I'm going to say, okay, u is x plus 1 to the 4, and v is x squared take 3. Okay. And now I can find my derivatives. So u dashed, derivative of this, so 4x plus 1 to the 3. And again, I have to use the chain rule within the quotient rule. But the derivative of what's inside the brackets here is just 1. So I'm multiplying it by 1. Alright, so that's all I need to do. And v dashed is 2x. So again, I've simplified like that. So now, if I find my derivative, so remember this is u over v. So f dashed x from my rule is u dash v minus u v dashed divided by v squared. Okay. So now I just take my functions and I put them in. Okay. So u dashed is this one, 4x plus 1 cubed times 1, I don't need to do that, times v, x squared take 3. One of the important things that I haven't mentioned so far is your brackets, okay? So there's no brackets here, but when I multiply, it's important to put it in brackets so that I'm multiplying by both terms. If I just leave it like this, it kind of says that it's this times this, take 3, okay? So the brackets are important. Minus u times v dashed, which is 2x, divided by v squared, so x squared take 3 squared. And again, I'm not asking you to simplify at this point, okay? I'm happy for you to leave it in that form. All right. Might do one more example. Okay, so let's have a look at this one here, 7x over 3x take 2. So even though we've got simpler terms, it's still an x term divided by an x term. Okay, so this one we would have to use the quotient rule. If we had, let's just say 7 over 3x take 2, You could use the quotient rule, or you could write this as 7, 3x take 2 to the minus 1, and then you could use the chain rule, okay? So some people prefer to simplify it like this, some people prefer to use the chain rule. It really doesn't make any difference, you'll get the same answer both times. So this is not the derivative, this is just a simplified form. So f dash x will be, multiply this out the front, minus 7, 3x take 2, decrease the power by 1. So multiply at the front, decrease it by 1, and then times by the derivative of what's in the brackets, which is 3. Now if we simplify that, we've got minus 21 over 3x take 2 squared. Okay. Now for this function here, because its derivative has this negative sign here, this function will have a negative slope for all values of x, because on the bottom line we can see it's squared. So no matter what value of x we put in here, the slope will always be negative. All right? Now as an example, let's just say that we did f dashed 1. Now f dash 1 will be minus 21. If we put 1 in here, 3 times 1 is 3, take 2 is 1, squared is 1, so it is minus 21. So f dash 1 is minus 21. So that what that means is at x equals 1, the slope is equal to minus 21. And this means that the function is decreasing, okay, going down. All right? A negative slope, meaning the function is going down. All right? Now, if we find, let's say f dash 5, for example, okay? Actually, that's a bit big. Let's do f dashed 3. So this would be minus 21. Put 3 into here. 3 times 3 is 9. Minus 2, 7. Squared is 49. Okay? Now, this is still less than 0. Okay? So the function is still decreasing. Okay? But this slope is a lot less than this one. Okay? So this is approximately equal to, got my calculator. So this is equal to negative 0.43. Okay. Alright, so the slope is still negative, but it's not as negative as it was before. Okay. And as we keep going, f dash, let's say 5, this will be minus 21, substitute in 5, 3 times 5 is 15, minus 2 is 13, squared is 169. Okay. And as a decimal, this is negative 0.12. Okay. So we can see that the slope is decreasing. Or we could actually say the slope is increasing because it's getting more positive. Okay. Now, the slope is always negative, okay? So the function is always going down, but it's going down at a decreasing rate. Okay, so this function, if we actually looked at what it looked like, up here, it's going to come down like this, okay? So as x gets larger and larger, as we put bigger and bigger numbers into here, this slope is going to get close to 0. It's not going to equal 0, but it's going to get close to 0, all right? Okay, so it's important to be able to understand, first of all, a couple of things. Substituting numbers into here gives us the slope, okay? If we substitute a number into the original function, then we get a coordinate, okay, an x and a y value. But when we substitute a number, an x, into here, we get the value of the slope, all right, which is an important difference, okay. Also, the meanings are different. So this number here, negative 21, tells us the slope is 21, and the negative tells us that the function is decreasing, okay, going down, all right. Now next week we'll look at a little bit more detail about what the meanings of increasing and decreasing are. We'll also look at finding the second derivative and substituting numbers into there and interpreting the meaning of those as well. Okay. Alright, so just a quick summary of what we've covered today. So first of all, you need to make sure that you are able to use first principles. Okay. in a variety of functions. Okay, so we looked at a quadratic, we looked at a surd function, we looked at a rational function. Okay, so make sure that you can do that. The second thing we looked at was the rules for derivatives. Okay, so I gave you that table. Okay, but I guess I want to just reiterate that I should be able to give you any type of function, and you should be able to find the derivative. Okay. Now, in this course, we don't look at derivatives of exponentials, logs, and trig functions. Okay, we will do that next semester in Advanced Maths 2. Okay. All right. So you've got first principles. So make sure you can do that, and you've got the 3 different types. Okay. Make sure you're aware of the rules for calculus. Okay. So the chain rule, the product rule, the quotient rule, and how to apply them. Okay. As well as the general rules that we went through. So if you want to practice, you can basically make up your own function. So I can say, okay, f of x equals 3x times x plus 1 to the 8. Okay, and I can find the derivative of this. So I look and I say, okay, this times this will be a product rule. Okay, so I apply the product rule as I did before. Okay, now I recommend that you practice a number of these. Okay. So I've given you in the assignment this week, there's like 8 or 9 different functions in there to find the derivative of. Now if you do those and you still aren't confident, remember there's heaps of questions in the textbook about finding derivatives and finding derivatives at a point. Okay. All right. So that's about it for this week. So I've condensed the whole lecture down into an hour, or roughly an hour. But obviously, you guys haven't had a chance to stop and do any questions, etc. Okay, so what I'm imagining that you're probably doing is you're either watching the whole thing and then you're going to go back and look at some examples, or you've been pausing it as you go and practicing some examples. Okay. So if you want to go back, feel free. Obviously, just scroll, pick out bits that you want to do, pause on the rules, etc. I would recommend that you do write down the notes from today, okay? So even though you've watched them, it's important to have them in your lecture notebook, okay? So that when you get to the end of the semester, you can have everything there, so you don't have a week missing, all right? Now, if you've got any questions during the week, remember that you can come and see me either in the help desk in week 9 or in week 10. Okay, depending on when you're watching this. Okay, so remember the help desk is Tuesday from 4:30 till 6:30 in B612. So you can come and see me there. Alternatively, you can email me, okay, if you've got any questions. And the other thing is, if you really want to, in week 10, you're welcome to come along to the other class on the Wednesday. And I'll also be available then if you want to ask me any other questions. Okay. So from here, what I'd like you to do now is to take your assignment. Okay. I recommend that you print it out because I want you to bring it in and hand it up. Okay. And I'm gonna have a look at it, and then we're gonna go through them as a class and answer any questions that people have. Okay. So print it out and then use the space on there to go through and answer the questions. If you want more practice, please let me know. Okay. All right, guys. Thanks for watching, and I will see you in week 10 or before if you need any extra help. Okay. All right, guys. Have a good day. See ya.